let me go to the next slide here. And so here's the roadmap for today's presentation. Basically, I'd like to educate the crowd, the general public, in terms of why satellite meteorology is educational, it's fun, it's useful, particularly to the CoCoRaHS community. You folks have been very invaluable in terms of providing data to a number of agencies, the daily precipitation reports. And what we decided about a year ago, is, in coordination with the CoCoRaHS staff, is to blend our website with the CoCoRaHS daily products and animate them. And I will show that to you in a couple of slides from now. I'm going to focus on the basics, just the geostationary satellites, the ones that you're familiar with on the TV weather broadcasts, but also the polar orbiting satellites, which are very accessible to the public and provide a lot finer detail than the typical geostationary satellites, and how they monitor the atmosphere, land, and ocean. And then I will show you our website at Naval Research Lab. It's called NexSat, and examples of some of the satellite products. And then I will provide a couple of training resources, a couple of websites that you can go to and get more information for satellites, weather satellites in general. And that this is an evolving field. And so under number 4, there is a new satellite, a new age weather satellite that I call. It's called VIIRS, and it was just launched recently, and I'll show you its capabilities and how it's wowing the research community and hopefully eventually the public as well. So what motivated us to provide this webinar? Well, you all have. There's 15,500 of you and growing. It's a very vibrant field of volunteer observers of a variety of types. I will try to keep my presentation to a kind of a intro or high school intro college level. So I'm hoping I don't overwhelm anybody with any material. I'm just going to try to keep it kind of basic. So within our website, this is what you see. On the left is the daily product. In this particular case, it's the February 4th U.S.-wide precipitation report, and basically it's measurements from 7 a.m. to 7 a.m. and we focus on the Central Standard Time, so basically the middle of the country. And most of you are pretty familiar with this, where the color dots represent the precipitation reports. And what we do is we try to blend the 24-hour animation. What you see on the right-hand side, now we're just getting into the nighttime with the pinks and the gray shades, and now we're into the greens and pretty much to tell the viewer the difference between the day and nighttime viewing. So it's a way of relating your reports to the actual cloud fields that you see within our satellite product suite. And on the left you see the products that just actually go into a little more detail with what NexSat can provide. So I mentioned we're going to discuss geostationary and polar orbiting satellites. So on the left, you see a polar orbiting satellite, and that arrow shows that it does go around the Earth and pretty much covers the Earth in one day. On the right-hand side, on this side, you see the GOES and the one that you're more familiar with it, but look how much further. This is 850 kilometers or 500 miles away from the surface of the Earth. That's the polar orbiting satellite. But look how much further away. It's about 22,000 miles or so away from the surface of the Earth, and that's the GOES. And there's quite a difference. There are drawbacks and strengths with each of those satellites. So this is a nice little cartoon showing initially the geostationary weather satellites. I'll animate this, and you can see the red dots represent the global coverage, of which the U.S. has 2 of them, goes east and goes west. And then you see the polar orbiting. There are many of them that cover and pretty much go as they're defined as polar orbiting. In other words, they go from South Pole to nearly North Pole and around the Earth, as opposed to geostationary. Let me play this one more time, and you can see that the red dots are pretty much fixed on a particular position of the Earth. It's over the equator. The polar orbiters move around from pole to pole. So just focusing on the U.S. side, again, we have the GOES West satellite and the GOES East, and you can see the entire coverage of the two. The GOES West allows us to see weather throughout most of the Pacific Ocean, and the GOES East, on the other side, actually you can pick up features in Africa. However, as you get along the edges, it tends to get a little smeared with the data. It's primarily the focus region is around this particular area here, and obviously focusing in the U.S. So these are some of the products that I'm going to present. These are the basic products. So this is a GOES East visible view that we provide on a daily basis at the Naval Research Lab. This is an infrared image. This is a water vapor image. A lot of you are very familiar with this because I think the broadcasters have been pretty good with bringing in water vapor as a way of monitoring the weather over your area of interest. This is another way of presenting it, and this is one of our products where you can see within the yellow circle the daytime conditions, and the background is fixed. It's called NASA's Blue Marble, and it gives a realistic depiction of what it looks like during the daytime. And then the nighttime conditions are more in the gray areas that you see on either side of that yellow loop. Here's a corresponding infrared where the color indicates the temperatures above a certain level. So that kind of, for forecasters or just people of interest, it kind of alerts them to where the more active areas of weather really are. Now, there is a weakness to the geostationary satellites in that it only provides coverage to 65 degrees north or 65 degrees south latitude to the pole. In other words, you do not see the polar regions with the geostationary satellite, and that makes sense because if you're looking out and you're positioned over the equator, you're looking at the edges as you scan north and south of the Earth, along with the east and west limitations. So this is a Google Earth representation. Again, we also produce products in Google Earth, where you see the white cloud field, and then you see the embedded regions of weather provided by particularly radar coverage. Now, we have been contracted out by Google Earth to provide the cloud field. We actually at NRL have done this, have provided this because we do have a real-time network of data that we can use and process. And so the user, when you click on the clouds that you see on the left-hand side, that's our product, and it's updated every hour. And we're actually contracted with Google Earth to do some more in terms of being able to extend that coverage over the polar regions using the polar orbiting satellites. So now the polar orbiting satellites, why are they important? Well, a lot of people are not very familiar with them, including the National Weather Service has just begun to incorporate polar orbiting data as part of their forecasting descriptions, forecasting briefs. Well, compared to geostationary satellites, they're a lot closer to the Earth. They're 40 times closer to the Earth, as I mentioned before. It's 500 miles, 520 miles away versus 22,000 miles away. And so you can imagine if you look out, if you have a window to look out over and you look out over the horizon and you try to look at, say, trees, a structure, if you do have leaves on your trees this time of the year, or as opposed to looking at something in closer range, well, you can do all kinds of magic with being able to view way out the horizon, but you're not going to pick up the detail that you can when you view something in the foreground. So you get sharper, more accurate detail with polar orbiting satellites. And we also have many more channels, and by channels I mean visible, for example, is a channel, infrared is a channel, water vapor is another channel, microwave sensing, and on. There's a number of different levels of different aspects that one can view via the satellite. It's not just visible. And some of them actually penetrate through the clouds. So the benefits, weather forecasting models have been greatly enhanced, and as a result of polar orbiting satellites, the forecasts have been greatly improved over a longer period of time. It used to be that you can make an accurate, fairly accurate forecast in 3 or 4 days. And over the past 15, 20 years, that's been improved out to a week to 10 days. It also provides atmospheric profiles, which is a very important component to forecasting and modeling. Sea surface temperature, as you see, global warming, and then monitoring all those different aspects that you see at the bottom there. So on the right is an example of a upper right there, the Aqua Air Sounder, and basically how the polar orbiting satellite moves along that red arc. So here's a graphic, a dynamic of how they actually move. These are the various polar orbiting sensors that are out there. Actually, there's more than that, but it's just to dramatize how they move across the Earth. And it's pretty much coming every 100 minutes or so. They come back to a similar position in the latitude of the Earth. Some of them go from north to south, some of them go from the other way. And on the right, you can see the coverage of the typical weather satellite. So as you can see, the coverage pattern throughout the day, there's a limited width. So regions of interest, for example, if you're, my hometown, Baltimore, you would pick up coverage from one particular polar orbiting satellite twice per day, one during the daytime and one at night. And now it's the one on the right's going kind of crazy with all the different sensors. And pretty much here to illustrate that we have the globe covered pretty well with these polar orbiting instruments. So this is the typical daily coverage of a polar orbiting satellite. This is what they call an AMSU product composite. And you do see gaps throughout the day typically because it does have a limited width, a limited swath, if you will, within the satellite coverage. So the black that you see is more pronounced over the equatorial regions, whereas the polar regions are all well covered because it constantly goes and revisits the pole every 100 minutes or so. And at the bottom here, this is just the daily display of the various products that we can get. Say on the left, it's temperature of the surface, sea ice. I don't want to elaborate on this. It was more just to impress upon you how the polar orbiting coverage actually looks. So in summary, what are the advantages and disadvantages of each? Well, on the geostationary side, the advantages is that you can view something every 15 to 30 minutes, and in fact, the next generation of geostationary satellites are going to let you view every 5 minutes or so. So there's a constant monitoring of weather, particularly the regions of severe weather and hurricane tracking. That's where the funding and that's where the interest really lies. Whereas the polar orbiting satellites, as I mentioned, over a particular city, for example, you might get just one per night and one per day. So in the red, you see, what is the best region for frequent polar orbiting coverage? Well, if you, over the past slide or two, you could probably guess that it's the polar regions because it keeps coming and revisiting that particular area every 100 minutes or so, whereas the U.S. regions, the mid-latitude regions, only get it, say, once or twice a day. The disadvantage of geostationary is that it's far away. It's 22,300 miles from the Earth, whereas in a polar orbiting realm, it's only 530 miles. It's very similar to, the International Space Station. And so we provide much better detail on the weather and climate. The geostationary satellite, every satellite only covers about a sixth or 25 to 30% of the Earth's surface. And I mentioned earlier that they have fuzzy edges along the sides, including the polar regions, whereas the polar orbiting satellites have nearly total daily coverage of the entire globe. Now, the geostationary satellites, as I mentioned, are limited to 65 degrees north and south, whereas the polar coverage, obviously, by its definition, is continuous over the poles, nearly every 100 minutes or so. And finally, there are a limited number of channels. So, for example, in the GOES satellites that we have over the U.S., there are 5 channels, visible channels, a water vapor channel, and infrared channels. There are several of them. Whereas the polar orbiting satellites, for example, one satellite that we've been using quite often for a lot of research and development is called the MODIS, or the Moderate Infraspectral Radiometer satellite, that's been around for, over the past 11, 12 years. And there are 36 channels, so you can pick up a lot of different aspects over the atmosphere, through the atmosphere, as well as the Earth. So what do satellites see? Well, there's a little cartoon depiction here. And first I'm going to have my little friendly satellite there in the center and what it actually observes along through the atmosphere and the Earth. On the left you see the sun, and the sun is the engine, it's the driver. It produces electromagnetic waves, of which we see, the human eyeball sees the visible part of it. There's a lot more to it. You have the X-ray on the higher side, if you will, and then the near-infrared information on the lower side. And so you get this incoming shortwave radiation, and it comes through and it bounces off clouds. Some of them bounce right back into space. Some of them actually penetrate through clouds and produce this diffuse radiation that you see with thin cloud coverage, for example. Some of them reach all the way to the surface. The snow reflects much better than, say, lush terrain, green terrain, which tends to absorb solar energy more, and water absorbs much more. But there's also response in that the land also transmits that particular energy back to space. And then there are these little particles that you don't see with the eyeball. It's the aerosols or gases. And again, they have absorbing and reflecting features, and basically scattering by the atmosphere. Now, on the right side is the Earth, and the Earth responds to the solar energy by emitting energy back in certain ways. So, for example, the water re-emits energy, the land re-emits it in a different way, and then there are all kinds of interactions with the clouds. So this is a cumulonimbus cloud, a thunderstorm cloud, if you will, where the tops of the clouds emit back, but there's also parts of the clouds that re-emit back to the Earth. And so as long as there's a balance between the two, there's a certain temperature, say a net temperature effect, everything is fine. But of course the issue over the past, say, 10, 15 years is this feature of global warming. What's really going on? It just takes a little bit of, say, imbalance between the solar energy and the Earth's response. In this case, CO2 has been a big player in that, to offset the constancy, if you will, of the Earth. And so global warming has become quite a big research issue recently. So weather forecast models, as I mentioned, greatly benefit from the recent advances in weather satellite technology. Here's a typical launching of a Ray-Winsan. It produces an atmospheric profile, and this is kind of sort of what we use. It's a skew T log P, but basically it shows the height, and then it shows moisture and temperature, and then also you can track the balloon, if you will, or the box, the Ray-Winsan sensor there, and it produces the wind field. Basically, as the box moves around, you can have some estimate of how the box moves, how fast it's moving over certain regions of the atmosphere. So this is what modelers use to describe the profile of the atmosphere. And it's vital for modeling. So back in 1973, with this particular image, sorry for the, it's a little coarse, but most of the dots that you see are Ray-Winsan launches, and they're launched either over water. Of course, there's a lot less of them there. And then there's a lot of these little green dots, red, and concentrated regions, and very sparse regions. And so they were the driving force for a lot of the weather forecast models. In 1979, we really started getting into the polar orbiting realm, the era. And you can see a dramatic increase in the number of observations. It went from 77,000 to over 32,000 observations. And then in the upper right, it's really been taken off in 1987, especially with the microwave imagers that are able to penetrate clouds and be able to provide a lot more detailed information about hurricanes. And then finally, now in 2006, there's over 4 million observations now. And the trick is not so much getting more satellite data, it's how to actually utilize the data because it can be quite overwhelming to ingest all this into modeling. So in summary, the weather forecasting models, what they do is, together with we still launch ravensons, obviously, but the satellites can also profile the atmosphere in a similar fashion. And then on the right side, we also have satellite products that you see here from a GOES sensor. And then the bottom, it basically, the two combine to provide a three-dimensional model forecast, which is very useful, obviously, a very important aspect in today's weather forecasting. One of the major funding and concern areas now is hurricane monitoring. This past year was a rather lack of hurricane activity, but as you know, hurricanes over the Atlantic can be very vigorous and of concern, especially when they're landfalling. And let's not forget our neighbors in the Pacific. There's a lot of typhoons. In fact, a lot more typhoons occur than hurricanes in the Atlantic. So a question would be, where would you locate the eyewall of this particular hurricane? This is it's the same timing, it's the same sensor. One is a visible, or actually this is an infrared, I take that back. And then there's another way of basically making temperature scales of the infrared. And one would guess that the brightest spot would be about there within that yellow circle that you see. Or it might be there. It might be, some folks would say, oh, it's developing on that side, on the southwest side, if you will, of the hurricane. Here, it looks like it might be here. So back in the early 80s, we started launching these microwave imagers, or microwave sounders, if you will, and they have the ability to penetrate through the cloud droplets and the precipitation. So you can see that it's really well defined. These are the same images with the same sensor, same location as you see here at the top. But look at the detail. You can definitely see penetrate through the clouds, the tops of the clouds, which in this case obscure where the core is, and they're very well defined within these microwave depictions, if you will. And so the actual answer up here translates to these purple circles. And you can see that that's quite a difference from where we put these yellow circles. And so the hurricane community now is actually revisiting a lot of what they thought were the center of storms. And that's a very important aspect in being able to predict where the hurricane movement is, because mispredicting or miscalculating where the eyewall is can lead to very erroneous results. Now I'd like to introduce to you our website. It's called NexSat, or it's the Next Generation Satellite. And there's our website at the top. It started in 2003 as a demonstration to upcoming sensors, but has become quite operational with a global suite of satellite data and products. So as the second bullet says, it has 31 sensors and models. And the thing that makes this very unique, apart from a lot of other weather satellite websites, is that it's near real time. In other words, we can get information in sometimes 1/10 of the time that the typical agency cannot. And that has to do with a lot of collaborative efforts with the academic as well as the government agencies. So it's very invaluable. The National Weather Service has picked up on our products and use that routinely. We also provide for a lot of field work, a lot of research. And then we also provide information to global agencies as well. We produce basic imagery as well as state-of-the-art imagery, and I'll show you some examples of those. And then we also provide animation capabilities, which is kind of a fun way of looking at the weather. So here's an example. This is just running through quickly. This is what the eyeball would see, true color, water vapor, cirrus. This is all over the west coast of the United States. Sorry, it's a little quick, but I should have tuned it down a little bit. But it gives you a flavor of the number of products that we can provide. Here's one that's very important, say, for the military aspects over regions of the world. Being able to distinguish, say, the high clouds in pink from the lower clouds in orange as well as in yellow from the snowfield in white. So you're able to do this all within one sensor, and it provides very invaluable information. You know, what is inside those clouds, or being able to distinguish clouds from, say, something on the ground like snow. This is a low cloud at night product, and basically the low clouds that you see are in pink. And this is just one representation using what I mentioned before as the MODIS data. And you can see this actually was last 2 Christmases ago. This is a very strong frontal event that occurred, and a way to distinguish the higher clouds from the low clouds that you see in pink. Now, this is an interesting shot. It's a visible image, but it's at night. So ever since the early 90s, the military has allowed the public now to view nighttime visible imagery, whereas before it was just on the classified side. So with a full moon conditions, you can see a number of features here. This almost looks like a daytime feature, but because of the full moon, it actually reflects a lot of the higher clouds that you see. And look at the detail that you see. This is very unprecedented as compared to, say, 15, 20 years ago. And you do see these little bright yellow lights, and those are the city lights that you see on the globe. But because the moon is so bright within a full moon realm, you only see a partial setting of city lights. And I'm sure many of you have probably seen these global city maps at nighttime vision. And that's all provided from this particular instrument. It's called the Defense Meteorological Satellite Project OLS, Operational Line Scan Sensor. This is a feature that actually cuts through the clouds in a razor-thin fashion. So this particular satellite pass ran from along this red line from northeast to southwest, and corresponding profile, it basically cuts through, and what we're looking at, what we're focusing in on, is the cloud profile. This was not available for researchers until 2006 with the launch of this particular satellite. And what's very beneficial here is being able to distinguish where is the cloud still elevated versus some of the precipitation regions. The modelers had a very misperceived view of how the world actually operates. They thought that thick clouds produce rain, and for the most part, there's a lack of precipitation coming out of a lot of the clouds. So this satellite helps out a lot with the research community. So how do you navigate through our website? Well, it's all mouse-driven. So first thing you do, say we click on the United States, and say you want to click on Northwest United States. So you come up with this particular image, and it shows up-to-date satellite product. In this case, the GOES product, GOES True Color product, if you will. And then you want to zoom in on a particular city, in this case Seattle, and look at the detail. We actually produce high resolution. This is a 250-meter resolution, or it gives you very fine detail of the snowfield that you see there, along with the terrain, the topography, and the just all the conditions that the geostationary satellites would not be able to see. And we also provide Google Earth coverage. This is just a little slant on how you can use Google to look at various aspects of our products. Speaking of Google Earth, we do provide global coverage as well. So CONUS at the top means continental United States. You have Europe, Australia, South America, Africa, and we're looking to extend our products into the Arctic and actually Antarctic regions to study things like global warming. This is an animation of the various regions around the world. You can animate just about every product in any domain, and you can see the again, the nighttime and coming into the daytime with the more green and yellows that you see. And that just shows you how extensive our coverage is with NexSat. We also provide a city view. Currently we have 81 cities, and we've utilized the MODIS high resolution, 250 meter or 2.25 kilometer resolution, and we provide true color, or with the eyeball would see out in space, as well as vegetation products, which is something that researchers are very interested in. And again, we also provide Google Earth capabilities. So for example, say you wanted to assess the climatology of Chicago, or the Chicago region. Well, those of you who are familiar that Chicago obviously would reside within the more grayish areas, the less vegetated regions, if you will. And you can see the vegetation, and you can see a lot of detail within that green. So this is a summertime shot. And then, of course, you get the fall colors coming in, and this is, I think this is an October, early October image, and you can see how the lushness transfers over to the changing of the fall foliage. And then the first snow that occurs, and you can see it's actually a brief snowstorm over this region, and it's just a way of being able to perform some kind of climatological approach for using high-resolution data over a particular city. We also do satellite volcano monitoring. Excuse me. One second, let me shut off the phone here. And this is taken from the International Space Station. So what you see on the left-hand side is an eruption that occurred a couple of years ago. And the region here is, the actual volcano is called Sarajevo. It's in the Kuril Islands. And so obviously with the Iceland volcano that occurred back in 2 years ago, we're very interested in being able to help out the airline community in terms of avoiding regions that would be harmful for air travel. So in our coverage, what we do is we have a lot of standard volcano sites that sometimes come on, sometimes come off in intensity. And then we have these red boxes. And those come from Air Force reports on a daily basis where the red indicates that it is currently active, and then we take away the active status once it's not. So this is very invaluable. It comes in real time. And it's a great way for the volcano community, along with the, say, the aircraft community, to basically focus in on regions of potential danger. And it comes in fine detailed information. There's a number of products to support where the active regions really are, any of the plumes that might be coming off of the particular site. And again, it gives you a Google Earth viewing option. So here's an example of that Iceland volcano. It was back in, this is an April 19th episode, and you can see what we typically look at, the true color. But forecasters and researchers are more interested in being able to have products where they can really key in on separating what is volcanic ash, what is the active area, how bright it is, how intense it is. So we have what we think is a state-of-the-art product, only here at NexSat, where we distinguish the volcanic plume versus the surrounding cloud field that you see here. And that can be very hard to do with other imagery. And so this, again, we think it's a wonderful new product, and the volcano community in particular has been using our products extensively. And then at the bottom here are all the active sites that you see.
Arunas, this is Henry. I wanted to ask you a quick question on the cities and the volcano views. Are those open to the public? Are they able to view this on your website, or is this specifically for certain users?
Actually, what I'm going to do at the end, yes, it's the answer is yes. It is the public it's open to the public. There are two little buttons in NexSat that I will show. I will demonstrate at the end of this talk that will actually bring up the city zooms as well as the volcano monitoring. So this is all on the public side. Yes.
Okay, great.
Good question. So to animate the Iceland volcano, this is one of our products, and again, we can animate this. And we use this color range that where the yellow, orange, red shades are basically the volcano, the ash plume. It's a little difficult. You need to be aware of the surroundings with this particular product to be able to distinguish the volcanic ash versus the surrounding cloud field. And on the right here, you see, for those who are familiar with it, this is a weather surface chart around a similar time. And you can see that the flow pretty much operates in the same way as this high pressure region. So basically there's a clockwise flow of the volcanic ash about the source, coming back to the source. So this is a powerful way of being able to show, highlight what regions would be of interest, what would be of potential danger. The problem with the Iceland volcano is, you probably know that a lot of Europe was shut down because they overestimated the extent of the hazardous plume that they thought would be encountered by aircraft, and really there was only a small percentage. So they're trying to rework that so that if any upcoming volcanic eruption occurs, they're not going to go haywire and shut everything down, because that costs a lot of money and downtime. Here's an example of us monitoring a fire, a huge fire that occurred in 2007 in San Diego region. I don't know if those of you are in the audience live in that area. Might be familiar with this. It was called the Witch Creek Fire, as well as the Harris Fire. It had it was very extensive, with unfortunately a few deaths and injuries that occurred. And this is kind of a depiction of where the red shades were the more intensive areas of that fire. So NexSat monitors this area over San Diego, where the yellow dots indicate the hottest parts of the fires and the red a little bit cooler. And actually the newscasters locally were using this as a way of showing the public how this fire was progressing and advancing, and we were kind of happy that they're using our products in that way. And then also fire agencies had they have their own tools, but they used this as a kind of a curiosity resource for their firefighting. What I'd like to be able to do here is bring this particular object up. It's not, that's fine. Okay. So I mentioned earlier that we have nighttime satellite views, and it doesn't stop during the day. So in other words, a lot of the detail that we used to get with visible data unfortunately was limited during daytime conditions. And as I showed you, there's actually a low-light nighttime sensor that's capable of depicting a lot of features, both through the atmosphere, over the atmosphere like clouds, as well as the Earth. So under full moon, these features come up in a certain way, in a certain fashion, particularly snow cover and clouds. With no moon, actually a lot of the terrain features come more into light. So you see features like fires, city lights, even lightning, fishing vessels, gas fires, volcanoes like the lava flows, if you will, the Aurora Borealis, and the snow cover actually goes away because it's not as reflected because there is no moonlight. So here's an example here's another example of a nighttime visible view, and this is over Korea. And again, look at the detail with the low cloud structure. And you can see the city lights, those bright yellow dots, and you can train yourself when you look at these from day to day or night to night, if you will, what city lights and what are not. You can see it here on the from the right side as well. And then you can distinguish, say, the stratocumulus clouds from other types of low clouds we have here. And then you can also, there's a lot of fishing that goes off the east coast of South Korea, and you can see those in bright yellow dots. NexSat also has online product training. So for example, for every product that we show on the website, there's an associated 3 to 4 page product training filled with a lot of graphics. And again, we're using it to basically show the high school entry, college entry level type of individual a 4 or 5 page graphics on products such as aerosol, being able to observe aerosol through the atmosphere, or detecting fires or low clouds at night. And there's, we probably have, I think, 30 different products, and so we have 30 different training tools. We also collaborate with Comet, as I mentioned at the beginning of this talk, and this is one of their modules that they use. It's called NexSat, Preparing Users for, actually now it's called JPSS, the VIIRS era, and you can actually register. You have to register through them, but it's very easy to do, and you can access the modules very quickly. And you start, and it's basically, in this particular case, NexSat, it gives you a 20-25-minute demonstration of its capabilities through that venue. Now, there are lots of users. In 2010, this is the user activity. On the left side are what we call the accesses or web hits, if you will. And you can see it running from January through December. And of interest in 2010 were was the oil spill along with the Iceland volcano. There people are really directed toward our website to monitor those particular incidents. And then typically within very active hurricane season, as it was in 2010, not so much 2011, you get individual spikes showing up through the summer months to monitor that type of weather. So in summary, this is, I guess I want to focus in on the daily average. We get over 230,000 hits on a daily basis of our products, and this number of visits, over 3,400, that indicates those users who spend more than 5-6 minutes on our website, basically doing animations, just spending a lot of time. In other words, those are the ones who are the curious, very interested public. They don't just want to see one thing, they want to browse our website for a lot of features, and those are the kind of people we really gear our products toward. So the final part of this presentation is that we're entering into this new era of weather satellites. There was it's called the NPOS Preparatory Project. This is the satellite. It was launched on October 28th of last year from Vandenberg, and it's operating pretty well. They're going through a calibration period now, but we're also receiving data and we're providing products, and we're getting started with it, and we're trying to get the show on the road in order to help the researchers and weather forecasters to be able to utilize a lot of the sensors that are on board this particular satellite. So we use this, I'll just call it VIIRS sensor, as a way of showing the improvements to edge of scan sensing. So this AVHRR is our standard. It's been around for a number of years, and it's a wonderful sensor, except that at the edges you get these kind of features here, very smeared, very blurred. And this is off the northwest part of the U.S. And the circle indicates, well, what is that? What are those dark areas there? And through simulation, you can see that they're lakes. They're lake river systems. So you can basically, the VIIRS holds its sharpness, its fine modality over the edge of scan, as opposed to the current AVHR sensor that does not. So there are a couple of examples that I like to show you. This is the new VIIRS sensor and the true color over the northeast U.S., for example. I'm sorry, this is, I'm saying this wrong. This is the MODIS sensor, something that's been around for a couple of years. And again, you see the edge of scan. There's some degradation that you see there along the northeast U.S., say over New Jersey, or not New Jersey, but you know, the East Coast region. And then you see the contrast, sharpness throughout the image that is very unprecedented within the satellite technology that's currently appearing with this new sensor. Here's another example of the Gulf of Mexico, again, very blurry with this MODIS product, true color product. And you look at the vegetation here, it's kind of a dark, dull green. And look at the clarity, the sharpness that you pick up with the new sensor, the VIIRS sensor. And NexSat is kind of state-of-the-art, and we're also one of the first to produce these products. They're just kind of coming online right now, and fortunately we have the capability of presenting these products first and being able to introduce the public to this great new sensor that we have. Here's another example over the southwest U.S. and Baja, California. This is a old Modus, and again, an edge of scan, looks very smeared, and VIIRS again shows the crispness of this. One of the features that we're very interested in, again, is nighttime visible viewing. There's a lot of research and a lot of new efforts coming into this. And so over Japan, over Tokyo, using the current technology, you have this the DMSP OLS that I showed you before over this region over Tokyo. And this is what it looks like when you blow it up. This is what the new sensor shows. I mean, it's almost as if you are, just 100 or 200 miles away from the surface of the Earth in space, looking down, or say flying on a plane, looking over Tokyo. I mean, it's just so sharp to be able to pick up a lot of the detail of cities. So here's another example over again, the northeast U.S. corridor, using the OLS. And look at the fine detail that you pick up with the VIIRS. And you can see the bright yellow showing the city lights. And a lot of it's not just city lights, it's also roadway lights. And you can actually map out highways using this particular sensor as well. Here's another evaluation over Maryland, my neck of the woods when I was growing up. And then also over this is the Bay Area, believe it or not. This is the San Francisco Bay Area on the left. This is Maryland region, Delmarva Peninsula, if you will, on the right. And look at the sharpness that you pick up here. I mean, you know where you are when you use this particular sensor. And this just came out over the past month or so, the processing of this. And again, on the right-hand side, you can see the cities versus the traffic lights, the traffic light patterns, and human activity. So, much improved sharpness with this new sensor. Here's another scene of Tokyo, and you can see the blow up. I'm just going to run through city to city here. You can see Las Vegas, and you can see that little nook indicating the strip. That was not available before. Los Angeles area, and you can see, and you can pretty much pick off features now, whereas before you would have to look at a map in order to produce the corresponding areas such as San Bernardino or San Gabriel Mountains. And then the San Francisco Bay Area, there's San Francisco, and you can actually pick up the bright lights within the Golden Gate Bridge over here on the left part. This is the Korean Strait. I showed you an example of the OLS sensing of it. And these dots here are the squid fishing boats. And again, fishing is a huge commodity. It's a huge activity over the east coast of Korea, and you can really bring that out with the VIIRS sensor. You can also pick up features like the Arctic Aurora Borealis. So, for example, the auroras show up in those nice little wavy lines that you see there in the northwest, and then also much more solid feature here in the southern part of this image. And then you can also pick up ice fissures. Now, features like this are interesting because from a global warming perspective, as you understand, the icebergs are beginning to break off from the main source and beginning to travel away from the polar regions. And then also these ice fissures are a way of being able to monitor the evolution of the ice pattern, the ice pack during the winter season. And again, that's very important to try to figure out the change in climatology within the Arctic region. So, in summary, I hope to have entertained you somewhat, and I hope to have provided you a better understanding of the weather and why precipitation measurements, why the CoCoRaHS volunteers are an incredible network of folks, and I hope that you're able to now relate what you do a little more with more appreciation, if you will, with the satellite technology. And I'd like to, if there's any future scientists, or if there are young folks, or even folks just interested in being able to educate yourselves with atmosphere weather and satellites, I really encourage you to look into this area because it is very vibrant, very evolving, and with a lot of need for research. And then I also described NexSat and providing tools of monitoring global weather and how the CoCoRaHS volunteers can relate precip to clouds over the U.S. And again, there's our website, and I just provided a couple of training resources here. I can provide a lot more at the end of this talk, and of course there's a very good research given by CoCoRaHS.org as well in terms of a number of issues, not just precipitation measurement. So actually what I would like to show you is one more scene, and what I will do is take this off, this presentation, and show you how to navigate to get to the CoCoRaHS site.
Arunas, this is Henry. We're going to let folks know, too, that we'll be posting your website on our WxTalk series page. So folks will have that on there for you to click on. And we're also recording this, and so if you want to go back and watch it again. So we're right at the top of the hour here, and we're extend a little bit longer to take your questions after Arunas is finished here.
Okay, and this will be very quick. And basically, this is just going through and navigating it live. So this is actually our website as it appears live. There's the top, the actual URL. And you click on this red box, and there it is. Pops up everything. And so basically, again, it's mouse-driven, allowing you to get to various domains within the United States. But for the purpose of looking at the CoCoRaHS part, you click on the entire United States region, and then under products, you go under rain totals, and there in the green, which is always green because it's always updating, you get the live accumulated precipitation ending today, February 9th, starting February 8th, and then the associated 24-hour animation. And again, you can see the cloud field associated with the precipitation field that the users of CoCoRaHS have provided us. So again, this is a great tool for the volunteers, and it's also a great tool for us, for the researchers, in terms of being able to relate clouds to something that's very hard to pick up, and that's precipitation measurements. And again, I can't stress the importance of what the users, the volunteer network, has been doing for precipitation database. So with that, I will hand it back to you and ask if there are any questions. I'm ready for that. Thank you.
Thank you, Arunas. That was a fascinating presentation. I think we've all learned a lot that we didn't know about satellites, and we really appreciate that. We've got a couple questions that have come online, and if you guys do have questions, if you would type them in at this time, we'll try to take, we're going to probably go, we'll try to go about 20 more minutes. And those that we don't answer on the broadcast today, we'll follow up and email answers to you on that. One of the questions that came in a little earlier was the satellite monitors Volcano. Could they monitor earthquakes? One of our viewers would like to ask.
The only monitoring, no. The short answer is no. Being able to monitor earthquake movement itself is not, as far as I know, is not possible. However, the Japanese earthquake that occurred last year, we are into disaster relief monitoring. So if there's anything like earthquakes or floods or landslides or things like that that are of interest to the agencies in terms of being able to monitor features, terrain features, we are on top of that. We develop a domain over that region. So, for example, the Japanese earthquake that occurred, the tsunami and the associated tsunami, we actually are still monitoring that part of Japan, and you can see the kind of the before and after terrain features using our satellite products. So that's we monitor it, but you cannot detect earthquakes with weather satellites as it occurs.
And there was a similar question about detecting tsunamis as well, and I think you kind of mentioned that there.
There was just a little comment about the tsunamis. There actually was a satellite sensor. It's not within our suite that is able to measure the height of the ocean surface, and they actually did pick up tsunami movement from that Japan earthquake over to the west coast of the U.S. And if my memory serves me correctly, they actually did use that, and it was a way of being able to track it, at least for one image, and time it with when it did occur over the U.S. And as you know, say just 40 miles up in Santa Cruz, there was some boat damage that occurred from the resulting tsunami. So I wouldn't say it was a valuable resource, but it was there.
Another observer or viewer question is that how often do the satellites get struck by objects and or radiation bursts that damage them, and what do you do about it then?
It seldom happens. There was a satellite, one of the sensors, NOAA sensors, that there was a sudden sunspot burst of energy that came and impacted the satellite. This was about 3-4 years ago. It did knock it out of commission momentarily, but then it came back online. It was kind of a wave, and they were able to repair that damage. But by and large, satellites, as with any other instrument, they are very well poised to keep them apart from colliding with each other.
Okay, I've got another question here, and actually two questions that are similar. How often are the geo and polar satellites replaced, and do the satellite orbits have a predictable decay rate, and what is their lifespan? So,
well, the beauty of the decay rate, for example, the MODIS satellites that I mentioned are an invaluable resource, and one of them was launched in 1999, and the other one was in 2004. And their lifespan was projected to be something like 4 or 5 years. I forget which it was, and they're still operating. There is some decay with the original MODIS satellite that was launched in 1999, but it's still going like gangbusters, and so is the current one. They call it the MODIS Aqua. And the MODIS Aqua, both of them are actually projected to continue providing coverage over the next 2-3 years. So there's a projected time frame which is very conservative, but then the reality is that the sensors, including GOES, some of them have a lifespan of about 10 years of operational use. So they've done us a very good job, and we're fortunate because it would leave us with a great void had they actually just served their time when they were expected to.
I've got a request if you could put your website back up on your screen. We're just looking at your background now. Folks had asked that.
Sure.
Here's another question. Can temperature variances such at metropolitan heat islands be detected with the capability of determining how much excess heat is retained and emitted by the city areas?
Let's see if I understand the question correctly. You're looking to monitor city emission of heat.
That's what it looks like, yeah.
Yeah, that's. I would love to be able to take a stab at that, but I'm not really well versed in that information. That's not something that we really do. Is monitor. We monitor more the aerosol, the dust associated with city activity, but not so much the temperature structure. So I better not answer that question, except I'll say I'm not quite sure.
Okay, another of our viewers here says, can you detect nuclear radiation?
I don't think so. Again, that's something that at least from my time period of monitoring the weather, I don't think so.
Okay, another of our viewers wants to know is, can the satellite image of clouds detect an impending tornado?
Yes, they can, but again, satellites are such that you don't want to take any particular product and just base your decision off of that. Satellites, as I mentioned, a number of different satellite sensors, and they all have a way. It's almost like looking at a prism. You look at a particular, say, a cloud from one angle, and then you look at it from another angle, and you look at it from a variety of sides, and a lot of them, what they do is they triangulate and get a good sense of the three-dimensional structure of a cloud. So, for example, in terms of being able to monitor an evolution of a tornado, there is a feature called a dry line that occurs, especially within Tornado Alley over the central U.S. And satellites are well adept to determining that dry line feature, and oftentimes they'll issue tornado warnings if it's sharp enough, if there's a sharp gradient that they pick up on one of the satellite sensors. So the answer is yes, they kind of do, but you also need the combination of radar, weather radar, to be able to fill in the entire picture.
Okay, here's a question from Pam in Oklahoma. She would like to see how you get the city view on the NexSat satellite page. So if you can show that. And
sure. And what I'll do is go back to the home page, and one thing I did not mention, I mentioned there are all these boxes, and every box is associated with a suite of products. One on the lower side here, you see the volcanoes. It has a nice little volcano icon, if you will, and then the cities. And I think the question was to bring up the cities zoom. So you click on that button, and here it pops up all the 81 cities. And these were subjectively selected. If there's someone, say, from the audience who's very interested in their city of interest, if it's large enough and it has, well, if it's large enough and if it's interesting enough, we'll put it on. So, for example, Baltimore is very cloud covered today, but let's see, I don't know, I guess we can pick up Albuquerque, for example, and show the true color image. Now, this is you're getting into the moderate resolution here, and then when you click on it on the screen one more time, you pick up the more detailed view over Albuquerque. Now, I don't have actually, one of the things we're going to work on is actually putting a crosshair so that you know exactly where the city lies. But this is the weather over today's Albuquerque region. And you can see the clouds as well as the cloud shadows that are associated around this particular region. So that's, as I mentioned, we get the true color, which is what the eyeball sees, but then, and here's another, let's see if we can bring up an associated, what we call biomass or vegetation product. And the green indicates more green, more lush areas, say, than the either the city or the more arid regions of a particular city, along with the cloud field. And that's pretty much what I'm going to say about that.
Here's a viewer asking, where does the funding come from? And with the current political climate, is NexSat in danger?
Good question.
Yeah.
Yes. The answer is yes and yes. It's the funding comes from the Joint Polar Satellite System, which is I don't know how many of you have basically looked over our satellite project. It went from this acronym called NPOS to JPSS, and there were a lot of funding and political issues that were occurring. This new sensor that I showed was actually supposed to be launched in 2006, and now it finally got launched in 2011. Funding was a big issue, and yes, NexSat is heavily dependent on being able to demonstrate that particular product and its features. What we're trying to position ourselves at NexSat is to provide the public with kind of a one-stop shop of satellite products. That helps us in the funding process because, yes, we're nervous. We're nervous that our sponsor is saying, okay, you guys have done your job demonstrating the upcoming VIIRS sensor. Now that it's here, what are your plans? What are your goals? So that's our plan, is to be able to use the various products. We have access to 31 different sensors, including VIIRS, and to keep ourselves afloat, if you will, and continue to operate, because there's a lot of users, as I mentioned, and it would be a shame to be able to, just get rid of NexSat just because they pretty much fulfill their mission. So yes, in short, the answer is we do have political issues, we do have funding issues, and we interact with our sponsors continuously about extending it.
Okay, we've got time for a couple more questions, which we've got on our screen here. How is the amount of data and observed data, satellite data, observed data, get crunched and how do the various weather forecasting models use the data?
That's a very good question. The satellites, what you see are pretty pictures right now on NexSat. Well, behind those pretty pictures are a lot of data. It's basically, as an example, if you show a visible image, there is a brightness count associated with each of those. There's, just like on TV, there are little boxes of information within, say, for even this particular image that we have here over Albuquerque. So this is actually if I remember correctly, this is an 800 wide by 800 high image. And so what that means is that there are 800 by 800 individual pixels associated with the making of this image. Well, each of them contain a kernel of data that you can backtrack actually and look at things like radiances. In other words, the amount of energy that comes in that gets emitted from that particular surface back to the satellite. And from that, the modelers are very interested in what is that intensity, what does it look like, and how does it interact with all the other sensors and their intensities. So you can backtrack and grab that data and then feed it into the models. And it's huge. It's an enormous task. I mean, it takes a lot of computing power. But as we know, the evolution of computing now has gotten so expansive that it's not that much of an issue anymore to bring in satellite data and then blend it in with, say, observations, human observations, aircraft operations, you name it. Trillions of pieces of information, feed it into the model, and run forecasts off of the model using this information. Satellites provide about 85%, I think, of the data that are used by modelers to make forecasts.
Okay, here's another question. Would your satellite be fried by an EMP if such was detonated above the atmosphere of the U.S., or have satellites been hardened to protect them from EMPs as well as solar particles?
Now, EMP is electromagnetic. I'm trying to remember what the P
I don't remember what that stands. Nolan, do you remember that one?
I don't remember the P part.
Okay.
Okay. I don't, and because I don't, I do know that there. This may be a completely different response from what the questioner wanted, but I know that there are different agencies, different groups of people, I won't mention them, that have been using satellites as target practice to launch and see if they can actually destroy satellites in the atmosphere. And the problem with that is that there's a great concern internationally, because if you do those games, if you will, and destroy a satellite, well, there are a lot of particles that fall from the satellite, and then, yes, they can get in the way of all the existing satellites, satellite field. There's a huge network of satellites just within the polar orbiting field. So I don't know if that was the actual question, but there is concern that target practice, for example, is not a good thing in the satellite realm.
And EMP, I was just informed, is electromagnetic pulse, is what the P stands for.
Right. Okay. Right. And that is a tool that has been used. It's not necessarily that you just have a bomb in place. You can actually use energy to zap a satellite. So I'm not that familiar with that, and I don't know the answer to that part.
We're going to take two more questions here, and we'll take the others off air and answer those. Let's see here. We have one that has to do with the drought in Texas. Has the progression of drought in Texas been able to be monitored via the vegetation observations?
The answer is yes. And again, we're not actually, there's a group from Oklahoma as well as from University of Wisconsin that use, actually this is the product that you see here is called a NDVI project. It's a vegetation index product, if you will. It's in green, and it does show the lushness of the terrain, and they actually use these types of algorithms, these types of scene depictions, along with other types of surface emission algorithms. We're just using this here in NexSat in order to look at the evolution of the lushness, if you will, over particular regions. So they do study drought conditions using products like this.
Okay. Actually, we'll take two more. Viewer asks regarding global warming, did scientists not know about this before the use of satellites?
Good question. The global warming issue, I think, pretty much surfaced back in the early 90s, and the Intergovernment Panel for Climate Change, the IPCC, had a couple of meetings since that time. There were a couple of articles in literature back in the 70s and 80s that did forewarn of situations like this occurring, and they did use CO2 as a way of monitoring through lab experiments, saying, oh yes, CO2 does contribute to global warming. But I would say by and large, most of the research community really got involved when back in, say, mid-late 90s through currently. And satellites, yes, satellites did provide a lot of information because they basically looked at the polar regions and said, hey, we're monitoring ice, and ice is disappearing. And over the last couple of years, there have been situations where they're projecting that Arctic ice will disappear completely in the summer by something as early as late, before 2020, which is just phenomenal. And they're using satellite data as a way of monitoring sea ice coverage between winter and summertime conditions over the poles for that. So I guess the answer to the question is it was raised back in the 70s and 80s, but yes, satellites definitely brought it to light in the mid-90s, if you will.
Okay, here's an entrepreneurial question out there. If we like to develop our own software products for commercial use, is there any satellite data available for this purpose, and if so, where?
Yes.
Okay.
Yes, there is a lot of. There is this conference that I've been going to over a couple of years. It's called Direct Readout, and the Direct Readout, basically, there are folks. Anyone in the public sector can actually download the data as a satellite comes over your region of interest. So if you have an antenna, you can actually pull down data, and a lot of folks, the concentration is over South America because they don't have a lot of the resources, the bandwidth, if you will, that say some of the more developed, the U.S. or European agencies do. So there is a what they call direct readout, and you can Google that and find more information. Also online, for example, the MODIS products that we grab, there's an agency in NOAA that provides a web resource where you can pull down. It's a massive amount of data. A pass takes up a couple of megabytes of information. It's called LADS, and I don't know what the acronym stands for, but it's LAADS. It's part of the MODIS network of data, and you can actually order, and that's the way we order our data sets, but you have to be pretty savvy in using the algorithms. And just one other point about algorithms is that we are also at Naval Research Lab setting ourselves up to ingest anyone who wants to develop a product that seems to be very suitable for research and development or state-of-the-art products. We are setting ourselves up to actually grab algorithms and then actually display them through what we call this new processing scheme that we're developing. It's just getting off the ground. It should be more mature by the end of this year, and we can actually, if I present this again, or if I can talk offline, we can actually grab algorithms and actually produce them via NexSat.
Thank you so much. Our last question, I'm going to toss it up to Nolan Duskin, our director. Nolan, do you have any questions?
Yeah, I've been chomping at the bit. I was wondering if
I knew you might be.
Arunas, thank you so much. This is amazing. And again, seeing that something so simple as our CoCoRaHS observations are being routinely fed in through your incredible high-tech system and displayed on a daily basis continues to amaze me. I got about 17 questions, but I'm going to limit it to one, and that is, I'm a climatologist. I did my schooling in the early 70s, and we were thrilled sitting around the satellite photography machine where, as I recall, every 30 minutes one picture came off that screen, and we would just marvel at what we could see of meteorological processes. But are there any products that have been assembled now that, for example, would give several decades of cloud cover perspective, where we could assess whether there's any systematic changes in cloud cover over time?
Oh, that's a big question. It's a loaded question. Yes, there is. And the answer is there's a complexity of resources that are available. I would have to Google that. Part of it, for example, the CloudSat era. CloudSat has been trying to provide a climatological sense of global cloud coverage and being able to separate the non-cloud, the non-precipitation regions from the precipitation. GOES, are the U.S. Geosatellites, also have a climatological resource, and maybe you're better positioned to answer that than I am. But I know that they've been, through NESDIS, the agency, they have been providing a climatological assessment of clouds over the past, for the lifespan of the GOES era. I'm thinking you probably have a better feel beyond that than I would.
And I would just say to those who are still on the call, and thank you for sticking around this long, everyone, but if you think there haven't been any improvements in weather monitoring and forecasting over the last few decades, wow, think again, because the forecasts are better, much better, and a whole lot of that is because of this ever-improved resolution that we have with satellite data. And then I'm just going to mention, this will be a topic for another webinar sometime in the future, but there is a new satellite mission well in the works that will very much affect CoCoRaHS, and that's the Global Precipitation Mission, GPM, where our rain gauge observations will likely be really, really helpful in the testing and evaluation of a radar or a satellite that will actually have the capability of estimating out-to-ground rainfall amounts. So that's coming down the pike, and we're looking forward to being a part of it. Okay, Henry, I'll be quiet now.
Oh, that's fine, Nolan. Arunas, thank you again, once again, so much. Really appreciate having you today. Our viewers really appreciate it as well.
I really enjoyed it.
Well, thank you, and we'll have you on again sometime. We'll talk more. Folks, as we end the webinar today, you'll as you exit, you'll have some questions, survey questions. We appreciate you answering those. Our evaluators we'll take a look at those and appreciate that. And then we invite you to join us for our next webinar. And that one actually will take place next week, next Thursday, same time, 1 p.m. Eastern on the 16th. If you have not registered yet, if you go to our homepage and you click on Message of the Day, you'll see that in the left-hand column. There's a link there. I will leave that up through the end of the day today. We're almost out of capacity, but if you'd like to get on that one, the webinar is on how climate data are used by Steve Hilberg, and of the former director of the Midwest Regional Climate Center. That should be as exciting as well. So until next week, we thank you again for joining us, and we'll say goodbye for today. Take care.
Thank you. Bye-bye.